Hello everyone, this is Riddhi Chaudhary from the School of Computing Science and Engineering, Calcutta University, and the course code of the subject is BSCS2380. The course name is Cybersecurity. So in today's class, we will read about primarily testing. Now let's see what is primarily testing. Hello everyone, this is Riddhi Chaudhary from the School of Computer Science and Engineering, Calcutta University. So in this course, we are reading about cybersecurity, and the course code is BSCS2380. So earlier we have started about learning about primarily testing. Now in this class we will read about two more testing, that is Fermat testing and Euler testing. So what is Fermat testing? It says that if any p is any prime number and a is not divisible by p, then a to the power p minus 1 is congruent of 1 mod p. So how we will do that, why we use that, we will see later in some example. To test n for primality, one simply chooses one base a and computes a to the power n minus 1 mod n. If a to the power n minus 1 is not congruent 1 mod n, then we can be certainly say that this n is composite. And the test also says that if after testing a variety of bases AI, we find that they all satisfy AI whole to the power n minus 1 congruence of 1 mod n, then we may conclude that n is probably prime. Okay. Another thing is, it is also known that there exist composite number that satisfies a to the power n minus 1 congruence of 1 mod n for all integers a that are not divisible by n. So these numbers completely throw the Fermat test and are known as Carmichael numbers. So we will so here is one example I want to give you for Fermat testing. Suppose I am having a very big number 2 to the power 50. So can I tell that whether 2 to the power 50 is prime or not? To know whether 2 to the power 50 is prime or not, we will have to first explore other things. Suppose I know that 2 to the power 16 is congruence of 1 mod 70. So now I can write this 2 to the power 50 in terms of 16. 2 to the power 16 whole cube dot 2 square likewise. Now what I will do, I will write it as 2 to the power 50 mod of 70. And this will be what? 2 to the power 16 whole cube mod of 70 dot 2 square mod of 70. So what we know that this is equals to 1. We already know that. Now we are having this one as 4 mod 70. So what we can write here, 4 mod 17, I have already told you in previous classes that if I am having the number less than any number, then we can directly put this. So you can directly put this as 4, or you can do the division and you can have the remainder as 4 also. So in this way we can have this, we can test whether this number is prime or not. So like if suppose we are having number of very large number is 4 to the power 532, 4 to the power 532 mod 11. So if I want to perform this operation, then how do I perform? I will write here 4 to the power 10, then whole 53, then I can write 4 square, and this is mod 11. Now why I have written that? If I'll test, I can found that 4 to the power 10, suppose I have tested it and I have this result as 4 to the power 10 mod 4 to the power 11 is equals to what? 1 mod 4 to the power 11 is equals to 1 mod 11. So what we know that 4 to the power n minus 1, that is 10, that is 11 minus 1, 4 to the power 11 minus 1 will also be 1 mod 11. So this will be 4 to the power 10 mod 11. So sorry, 4 to the power 10 is equals to 1 mod 11. Congruence of. So from this we can conclude that if it is 1 by 11, so what we can say, this will be 53, and this is 4 square mod of 11. This will be 8 mod of 11. Now the remainder will be 8. So from this we can conclude whether a number is satisfying the Fermat's theorem or not. Now here also we are having different examples, as we can find out different numbers, and we can compare these numbers in terms of A and B. So what does this A and B means? That if you are having any number x to the power n minus 1 is congruence of 1 mod n. Right, from that we can identify the same thing for the large numbers, the modular division of the large numbers. Now before going to the theorem of Euler's, we first need to know about Euler's Totient function, and Euler Totient function is represented using phi n. It is what does it represent actually? So what does it represent? It is the number of integer that is less than n which are co-prime. So that means if I am having that 37, then I will have from 1 to 36, every number will be co-prime. Right, so here are the numbers that are less than 35, and these are the co-prime numbers 1, 2, 3, 4, 5. So if I'll find out the co-prime, I will only consider the co-prime numbers. What are the co-prime numbers? 1, 2, 3, then 4, 6, 8 all are divisible by 2 and 3. 6 is divisible by both, so we can ignore that. We can ignore 9. Then here comes 11. So 1, 2, 3, then 11, then 13, then 17, then 19, then we can see 23, then we can see 9, 29, then 31, then nothing. So what are the numbers we can see? And these numbers will be co-prime to each other. So we will find it out as there are 24 numbers if we are having 24. So now for a large number, it is not possible to count down all these numbers and then find out the co-prime numbers. So what we actually do for the large numbers, what we do, we basically follow this rule that if a number can be represented using two prime numbers p and q, then the Totient function will be equals to p minus 1 q minus 1. So we can take any example. Suppose we want it for 21. So what we will write, it will be the multiplication of 3 and 7. So we can directly write it as 3 minus 1 and 7 minus 1. If we'll find here for 3 minus 1, that is 2, number this will be 2. And in 3 also there are two co-prime numbers are 1, 2, which are co-prime to 3. So likewise here also you will find this one here as 6. and the result will be 12. So what will be the integers that are co-prime to each other? These are the integers as given here: 1, 2, 4, 5, 8, 10. Likewise, all the numbers will be co-prime to each other. So here also we are having many numbers, and the total number will be of 24. Right. So now the numbers which are having GCD is equals to 1 can be considered as co-prime numbers. Uh, so now the Euler's number, we can apply Euler's numbers in different ways, as you can see here. Okay, we have given one number 81, and 81 can be written as 3 to the power 4, which is equals to 1 mod 10, right? So what we can do for 2 to the power 10, we can write it as 1024, and this can be written as this. So now if we are having two numbers which we want to find out, okay, what would be the Totient number of this. So what we can have, if we want to find out the co-primes number, then we can directly multiply and have, suppose we are having 12. So what we can write, we are having 4, we are having cross by 3. So this can be written as 4 minus 1. We can directly write it, because this will be very helpful for large number. This will be 3 cross 2 is equals to 6. So for any number we can have this Totient values, which will be very helpful to find out the number. So here you can see that the Euler's theorem states that A and if A and N are relative, then a to the power 5n is equals to 1 mod n, which I already explained. That means what? Okay, if I am having, suppose a to the power a is equals to 3, n is equals to 10, that means 10 is having 5 is equals to 4. How can I have that 5 of 10? I can write, so this will be 5 of 2, this will be 5 of 5. So what I am having, 5 of 2 is equals to 2 minus 1, 5 of 5 is equals to 5 minus 1. So this will be 1 cross 4, that is equals to 4. So I can write here 4. Now what I can do, a to the power 4, that is equals to 3 to the power 4 is equals to 1 mod n, that is equals to 10. So this will be definite. From that we can identify any number and we can test whether the number is prime or not. If I'll get this result as 1, I can can be sure that this will be a primary number. I will also have an idea about the prime numbers also, okay, how these numbers uh, are being allotted, or how we can have the prime numbers. We can identify the GCD as well from this number amongst different numbers. So here we can see one property of this, okay, if we are having ax mod n, that can be written as 1 to 5 product of xi, and this is equals to what, we can write it directly. We can shift the mod part here. As you can see here, the initial equation was this one, and we can directly can shift the mod part here, and now we can do the proof as this is a to the power, this is a to the power phi n cross. As this is constant, we can take it in the outer side, so we have taken it as common, and we have written only the xi part in the cross product, and this will be similar to this one. So as these are similar, we can ignore that, and we can directly we can divide it. So the result will be, for similar, as these two are similar, the result will be 1, and this is 1 mod n. So likewise we can prove that whatever we have said earlier is true. So this theorem can be written alternatively using phi n plus 1 is equals to congruence of A mod n. So this is also valid, and this is what Euler theorem does. These are the references I have taken for all these lectures. Thank you very much for today's class.